right? And it's going to be broken into these k coordinates. Q1, Q2, up to Q. Okay, and so Qj is going to be somewhere in here. So it's going to have k coordinates, because remember it's going to be in this k-dimensional space. And so for each of the coordinates, so for Qj is just going to be P dot product with the dot product with Uj. This is Qj, right? So I did this for each of the coordinates. So in order to get Qj here, I just took the dot product with Uj. So I can create k of these Gaussian random variables, normalize all of them, and then I take the dot product with each of them. Now, if you remember how the dot product worked, what the meaning of the dot product was is I thought of each of these as this point, as this vector here, and if q or u is this unit vector, then the dot product is just with q. If q is the length of a unit vector, then projecting onto q is just the length along this direction. And the length along this direction is the coordinate in this one-dimensional space. Okay, so the other thing is when I do this projection, this length is always less than this length. It's always shrunk because I'm projecting it down. I'm squashing it. So it's always shrinks, and in fact, the expected amount it shrinks is going to be 1 over d. Because it had d dimensions, now it has only 1 dimension. So actually the squared norm expected shrinks. Yeah, this should be a square root d over k. So the expected shrink is 1 over square root d, turns out. So I want to inflate this back up. So when I glue k of these together, it has the same expected length. So you need to multiply it through by the square root d over k. Okay, and if I do this, where I set k equals to this, I get this guarantee with some probability. And you can increase this factor and increase the probability that this happens. Okay, so it turns out you can do the same thing for approximating the matrices by projecting onto some subspace. The projection operator for matrices, again, will look something kind of like this, and you need to have, again, the square root d over k scaling term here. Like you multiply every value by this. But you can do projection with matrices where this R is now a matrix. You need to flip this. Doing columns instead of rows, you need to take like a transpose of this. But this projection is a very simple operation, and it guarantees this airbound property. Okay, so this is another kind of technique. Again, this to get epsilon error here, this term needs to be pretty large. So to get 1% error, this is like 10,000. But what's cool is that this is independent of what the original dimension was. It only depends on the log of the number of points. So if you have, so that there's some things in machine learning where you get these what are effectively these infinite dimensional spaces. But maybe they're not infinite dimensional, but you can think of having some extraordinarily large number of features, some unbounded number, and you can kind of get them to be a finite number of dimensions using this technique. It only depends on the log of the number of data points. And then there's some error term here. But so this is really pretty amazing that you can do this. So and again, you can use this for approximating matrices, but this bound, the 1 over epsilon squared, is not too different from this bound for t. They're both pretty large compared to this frequent directions technique. So again, this was comparable to the state-of-the-art technique row sampling until just a couple of years ago with this newer algorithm. So then Wednesday I'll talk a little bit more about how to use MATLAB a little bit, and we'll talk about some other really cool stuff with compressed sensing, which will do some other randomness projection ideas as well, kind of related to this.